I'll start recording. Okay. This is what I got.
All right. Yeah, we did our things. Yes.
Okay, let's begin. So yeah. So after this week, we'll be doing coding. So today will be the last lecture where we discuss with you and how models work. And after that, it will be you divided into projects, and you'll be coding your own models. Obviously, we'll be helping you, but yeah. So okay, let's begin. So we just import a basic bunch of files which will be required by a model. We require TensorFlow, Keras, NumPy, and Matplotlib for plotting graphs, as you may have learned last lecture. And just ignore this one. This for just a visual stuff. Okay, and then we are taking the MNIST dataset where we'll predict numbers like there'll be digits from 0 to 9, and we'll be predicting which digit actually it is. So okay, let's so we have a data of 60,000 images with each image of 28 by 28 pixels. So we'll load them into a array of 28 cross 28 2D array. And since each pixel value is from 0 to 25, 0 being the black and 255 being, 0 being the black and 255 being the white. So we load them into 2D array and with 0 to 255 as values. So you can see an example array of an image. This is like basically this image loaded as an array up there. I can show you a better example. So see, this is, I created this image and this looks something like this in an array. I represented ones with anything that is not 0. So basically this looks exactly like this, but with different pixel values at each place instead of 1. Do you have any doubts till now? Or should I move on? Have any concerns regarding how it reads the image or how we're getting this 28 by 28 array? Anything? Okay, that seems yes. Okay. After this, I took some like this. These are the sample images of our data. So we have a 5, we have a 0, we have a 4, and like 60,000 images like these. And then we'll train our model based on this. No. So Rundal, you said pixel value can only be 0 or 1. No, pixel value will be from 0 to 255. But I coded this thing as like if it's 0, it will remain 0, and if it's anything other than 0, it will 1. It will be 1. So like 0 representing all the black shades and the darker ones, and 1 is anything which is slightly colored. So you get a 5 here. But actually it will be something like this, if you can see, but it's not giving a proper shape since you can't print 28 there. Does that answer your question? I'll take that as a yes and move on. Okay.
I have a question.
Yeah, sure. Go ahead.
So like, where's this code being run? Like, is it being run in the browser or?
It's a Jupyter Lab. It's run on my laptop. So it's hosted on my laptop. But yeah, you can use, I've set it up in Google Colab as well. So it's in our team drive. I hope you are a part of the team drive.
Oh yeah, I think so.
Yeah, you can open there also, like you can see it as we go.
If anyone isn't, reach out and we will help you out.
Yeah. Okay.
Wait, how do I access it? What did
Okay,
I get?
just okay, I'll quickly share that thing. we'll find a shared drive, BigThink AI with BigThink AI, and it will be this one. And open with a Google Colab.
All right, got it. And you can just like write code on here and everything.
Yeah, this is the entire thing what I have in my notebook, which is locally. But this is the entire thing. You have access to all the code. But yeah, you have to change this. Like this was image hosted on my laptop, but to host another image, you can upload it here and just change the address here.
Okay, all right, got it. Thanks.
Okay, is that fine?
Yep.
Okay, moving on. So these are a bunch of examples of our data. And yeah, I'll share the link to the project. So our neural network is basically, we'll be converting a 2D in the first layer, which is a flatten. We'll convert a 2D layer into a 1D array. So basically 28 into 28 pixels will be converted into 784 values. So then it is passed through two fully connected dense layers, where the last layer has 10 nodes and a softmax activation function that will indicate the confidence prediction, which are values ranging from 0 to 1. It will give, like, for example, it will give values for each of the 0 to 9 numbers. So like, for example, if 0 has a prediction of 0.01 and 1 has prediction of 0.02 and so on. So like 5 has a prediction of 0.8. So that's the highest. So it will predict the number in the picture as 5. Okay. And this is like the layers. This is the entire model. Basically, there's 3 lines. That's it. That's the entire thing. And then we compile the model, and then we test it with 10 epochs. Like you were doing 100 epochs on the thing with the playground, TensorFlow Playground. Here we'll be doing on just 10. It's like pretty easy because it's nothing but just digits. So yeah, so basically what epoch is, like we are just training 60,000 images again and again. So basically we'll be training on 600,000 images, but only 60,000 will be unique images. So if we if we train on too many epochs, it will be training on same images and learning too much about those images and try to replicate the results of those images. So like if you draw one in a certain way in these 6,000 images, it will try to find that kind of writing in other test images. So it will spoil the result. And if like it's too small, it will underfit the data, so it won't able to guess or predict what the number actually is. So we should have a safe amount, but that amount depends on the data, and it's not like a 10 always. It depends on the data and what model you're using. So it actually you have to try and test it, which epoch best works for you. So this is the accuracy. Accuracy is with what accuracy our model is predicting the correct. It's a correct data in the picture, like it's a correct number. So after we test the model. So you'll be seeing a loss. I'll be talking about loss in a bit. So we get an overall model accuracy of 95%, which is okay. We can improve on this. How can you guess anything? How can we improve on this? By looking at, this is another model down there. So if you can guess something, what's different than the above one? Anything? Yeah. What else? That can help. What else can change it? So okay, I'll go ahead. So what we'll do is we'll divide each value by our data by 255. Increasing number of neurons would definitely help, but we'll be having the same layer with the same number of neurons. We won't be changing that, but we'll be normalizing our data. I'm just talking about it. So we'll like we have values from 0 to 255. So that's a long range of values. So what we'll do is like divide each of the value by 255. So all the data will be between 0 and 1. So nothing will be like if a pixel value is like 255, we'll divide it by 255, so it gets 1. So like all the values will be between 0 and 1. How will this help? This will help our data to just focus on like the range of the data will decrease, and the production, like the processing of the computer, the network will increase, so it will able to train better. So if you can see, like we trained on the earlier model, we got a 95% accuracy. But when we train with the normalized data, like after dividing it by 255, the trained data, we get a increased accuracy of 99%. You can see that here. That's the test accuracy. Yeah. So how does test accuracy differ from the train accuracy? Can somebody tell me, or like somebody knows?
Who pick me? Kidding. Come on.
Yeah,
Someone.
you can go ahead.
No. I'm kidding. Does someone wanna
Yeah.
have a shot at it?
Yeah, it differs on test data and train data. So what is this most significant difference between test data and train data? Yeah, correct. So the model has tested on like has trained on the train data, and it has seen it like 10 times, like each image it has seen 10 times and learned more about it. But what is trained it the test data, it's like a fresh data set which the model hasn't seen yet. So it will obviously have some less accuracy than the one on which it trains, because it has seen it over and over, and it increases as you go on. So as you can see the difference, that's why the difference increases between the test accuracies and the train accuracies. Okay, and let's now talk about the loss. What's loss? So anybody knows about what is loss?
Wrong predictions.
Yeah. So can you see this image?
Yeah.
So yeah, basically what we are doing is just give me a sec. So what we are doing is basically giving bunch of y values and x values, and asking the model to predict some value of m for us, which is the like slope. That's the like basic, the simplest term of what machine learning does. So we give them x values, y values, and we ask them to predict the value of m. So as you can see in the model, we were feeding the model x train and y train. Y train was just zero to values from 0 to 9. So like what each image represents. So as you can see in the bottom 5, so this is like the bottom, you can see the little 5, that's the y value. That's the actual thing it will test again. So like if it will see, it will run the model on the image 5, and it will then see if it corresponds to the y value of 5, which is this. So the x value will be the image, and the y value will be the single number 5, like 0 to 9, the digits. So basically we are feeding it like a bunch of images in X, and trying to equate it to single number 0, 1, 2, or 3, or 5. So like for example, let's like suppose the function gives us like this slope, and these like E, B are bunch of numbers. Like, so what loss is basically the distance from the predicted value, this is the predicted line. So these are the distances from the predicted value. So like the total loss of this function would be like 5 plus 2 plus 1 plus 3. So this distance from each number, what it's predicted, that's the loss of the model. So as you can see, while training, our loss is 0.1840. That's for 60,000 images. So like 60,000 data points are like almost near the line, and 60, like the difference between the predicted value and the actual value for all, like added for all 60,000 of them, is like 0.184. So it's like pretty less, but we can obviously improve on that. That's the loss. So I'll stop here for questions, and go ahead if you have any question till now, then we'll have some fun.
This is just for like
Yeah.
my own understanding. So from epoch
Okay.
9 to 10, it has a
Mhm.
higher accuracy, so it's getting it right more of the time. Or when it's getting it wrong by just a little bit more. Is that what that's saying? Because
Yeah.
okay.
Basically, it's the distance from each point. So like maybe like let me show. Maybe the distance is like increasing or decreasing. So like after model, like it reevaluates the m value to be this, and after this is like suppose E1, like epoch 1, and after that it sees like it's more fitting like this. So like see, the distance decreases, but from some points the distance increases also, right? So it depends. And like the best case would be like just joining all these points, but that will be like overfitting. So like if we test the data with some point like lying over here, so it won't help. So we have to have something which suits all of them, plus the data which will come later on, like as test or validator, or like when we implement the data in real world. Does that answer your question?
Yeah, thank you.
Okay. Oh, anything else? Any doubts? Anything you want to go over again? Okay, I'll then move on. So after we took images as a data, we converted it to an array of 28 by 28, then fed that into a model, and the model predicted whether it's a number or like if it's a number or like what number it is and what the accuracy it is. That's how like we have, that's the how a model is, like the whole complete thing is made. So like data, we have data, image, we have a model, we have some pre-processing, we have output, and we then test a model. So now we test a model. So this is an image that I created on MS Paint, and then I uploaded it here, and I tested the model on this. So you can see that. So with like when we normalize the model, we get a it predicts a number 5 with confidence of 99%. So it says that I'm 99% confident that the picture, the number in the picture is 5. That's what the model says. But like when I use the normal model, which is not normalized, like which is the data is not divided by 255, here we get like the predicted number is 8, and with the confidence of 0.37. So the model says like, I don't know, it's like it's an 8 with a percentage of 37%. So yeah, that's the difference when like after training and testing it. So let me show you an example. Okay, let's draw something. Let's say we drop 1. No. Much better. We resize it to 28 pixels. Yeah, it's fine. And it's saved. And we
Be 28 pixels.
what?
It has to be 28 pixels.
We have taken a model with the 28 pixel image, but we can change that to anything. So if we limit our data to, like, you can see the input shape is like 28 by 28. We can we have limited to 28 by 28 because it has less number of pixels and it can get we can train it easily. But if like you can increase the pixel value also, and then it will be harder to train the model because it has much more number of values. So like if it's like 280 and 280, we'll have like something of the order of a 10,000 like digit number. So more than that. So it will be harder to train the model on that number of values because like the array size will increase drastically. So we have limited to 28 by 28, but like obviously we can increase it to whichever suits us.
Okay, all right, that makes sense.
Yeah. I'll just copy this. It's a bit laggy, sorry. Yeah, not that good. It predicts it predicts it as 2 with 93% accuracy. So yeah, we can obviously it's not that good, but yeah, we can train it further and we can like have bunch of different shapes and like yeah. So you can try it out in Colab or like you can run it on Jupyter Lab if you have that, or you can even do it on PyCharm Professional if you have that. It will run on everything. And if you have any doubts or any help, you can ask me. And what we can do to improve this model further to have more accuracy.
Increase the neurons.
Yeah, no, yeah. Obviously, after that, like we can do that to a certain stage, right? Mm, okay, I'll just go ahead and tell you. So we can use a different type of model. So we would use till now we were using feed-forward network, neural network, and now we can shift to convolutional neural network. Rohit will be telling you more about it in a bit. So that will drastically increase our performance because it's the design of that model is such so, and we'll be using that in our project. So you'll be getting to know about it more, and I guess you should really like it better than this because like you'll be needing just 5 epochs to train it to a 99% accuracy. So yeah, Rohit. So Rohit, would you like to continue things up? Or do you want to do it in the next lecture since the time is already 6?
I mean, I have time, but you know, other people
Mhm.
probably don't. So
Yeah, there's Rohit. He has muted himself. Um, so yeah, if you have any doubts or you want to play around with it, You can do it in Colab, or you can ask me to do it and I'll just do it.
I'm so sorry, guys. My network timed out.
Ah,
Should I take over
yeah.
for the next part?
Sure.
Okay, cool. All right. I'm back. Essentially what Siddhesh just showed you is the first way that we often learn to solve this problem with machine learning, which is where we directly take all 28 by 28 pixels, right? So that's 784 pixels, which we turn into a one-dimensional vector, just all the way down. And we have 784 input neurons. And that's fine for small pictures, right? And you saw like, he had to shrink the one down to 28 by 28 because the model isn't built to handle very big images. So what we usually do in the case of bigger images, and in the cases like video recording, footage, document scanning, things like that have a lot of information that can have a lot of values, we just look at it part by part. And we're going to get to how we implement that. You can go back to like last week's slides if you want. And if you have any questions, of course, always ask. But we will be walking you through how to implement the next level to what Siddhesh just showed, and that's the convolutional neural network. We're going to put this example up as well. So we have a problem. You're familiar with it, hopefully by now. There's 0 to 9, right? And Siddhesh called them Y-train. We're going to call them a few different variable names, and we're using slightly more like simpler syntax, but you can get more and more complicated to like the level that Siddhesh just presented, because that's how it's usually done. We just made this sort of like everyone to be able to quickly grasp. But essentially you have 0 to 9, and those are called the labels or the Y-train, as Siddhesh just showed. And that is what you need to bucket whatever image you see into, right? When you're running a Colab, by the way, we always have this little runtime instruction. You're going to see it in the project as well. But you always want to connect to hosted runtime. And who's hosting it? Google. Because their lovely, lovely work is democratizing AI. So it's pretty awesome. All right, it's going to take a second. All right, it says connected. It shows how much RAM and disk space we're going to be using. We can change the runtime type. Don't worry about TPU. That stands for Tensor Processing Unit. There's some extra commands you need for that, but that runs the fastest. You can run with none, or you can run it with a GPU. So we'll just run it with a GPU because convolutional networks take some computation, and we'll see why. Okay, starting off, we have to import our libraries. So I'm just gonna walk you through it really quick, bit by bit. This here is just a repository of data sets that the folks at TensorFlow at Google have sort of compiled for everyone to download from and learn machine learning, the basics of machine learning. And it's really cool. You import that repository, which is called TensorFlow datasets. Yeah, don't worry about Logger. There's a lot of stuff that you can just skim right past, because the juicy stuff that you guys need to work on is down here in the model. And we'll show you, like next week, we'll just show you the project and you guys can get started. So we're downloading the data set, and we're downloading some extra information about it so we can see what exactly goes into the data set. And we are splitting it into a training set so that we can make the model learn, and a test set that the model doesn't learn. Unseen data is test. Data set MNIST downloaded. So we can move on. All right, so now from the data set, we actually have the class labels already in there, right? And the classes are either 0, 1, 2, 3, all the way up to 9, because there's 10 digits in this problem. So we can check using this block. Don't worry about this syntax. These are like data science libraries and stuff, matplotlib, and you don't need to worry about it yet. Maybe in the future, not for this semester as of now. But we can see that we have 60,000 training examples that we're going to learn from, and 10,000 test examples. If those numbers look familiar, you have a keen eye, because it is the same data set that Siddhesh ran his model on. We're using the exact same data set. We're just approaching it with a different network that can handle things that are bigger. So for every image, so this is a for loop. We're just taking 3 images and we're printing the image size, just to show you guys what the dimensions are, 28 by 28 by 1. Can someone tell me, I'm going to keep asking this because this is something that it's easy to get confused about. What does the 1 mean? I assume we know what the 28s mean. Does someone want to tell me what the 1 means in that image, in all the images? Any takers? Oh, in the chat. 1 class is not it. It is 1 color channel, 1 out of 3. So we are, the MNIST data set is in monocolor, and you can recolor it. Siddhesh made it purple and yellow. You can do all sorts of stuff with it, but it is monocolored. It is not running R, G, and B to give you the range of colors you can see on a computer screen. So we're just taking in that as a 1-dimensional thing. Now, the total dimension of each image would be 28 times 28 times 1. So you can sort of treat it like a 3D thing for now, but that's not that important. All right, so processing the data. Last week, Chanel talked about some common ways in which people process data. This MNIST data set is pretty normalized already, and like everything is in the same size of image. You don't need to resize images and everything. It's pretty clean. There's a version of it which is called MNIST corrupted. That's like for the people who are asking for trouble. So you normalize the images, which just means, like, so they showed us, you take all the pixel values between 0 and 255, which is the normal range, and you're just compressing it down into a range between 0 and 1. And that makes it easier for the model to process what's going on. You're just converting it to a tiny decimal instead of like some big number. Oops, I ran that. I need to run this. Yeah, so you can either hit run all once you're done with the whole thing, or you can just run everything cell by cell. That's how this environment works. Colab works like that. So we can plot out a few images. They're familiar. This is like the original color scheme. Siddhesh made it look cooler. But that's how the numbers look. And it's messy, right? Human handwriting. I can't tell if that's a 1 or a 7. I've looked at it several times. But yes, now we are at the model. We need to build a way to accurately, like, we're pushing for accuracy here. And there's dangers to, pushing too much accuracy later on that. So the syntax that we're using, we're just getting Keras, which is one API that can write really readable, like, you can read this and sort of understand what each layer does. So Keras does that within TensorFlow. But if you're doing this on TensorFlow alone, you'd have to write like a lot more code, and it doesn't look as clean as Keras. But these are just libraries within Python that have all these inbuilt, objects. So you can create a model, tf.keras.sequential. If that looks familiar, that's because Samrat mentioned that that's one of the 3 main functions you need to know to do the project this semester. This is the CNN part of the model, and that just means the convolutional part, which is essentially I use this phrase every time, but that's because it kind of makes sense, at least to me, and I hope it does to you. It's just like scanning across an image bit by bit until it sees the whole thing. You're just filtering across it. So there are 2 components to that. You have conv2D, which is 2-dimensional. You're like using a square to go over, a tiny square to go over a big square as the flashlight. And then max pooling, whatever information it gathers from that tiny square at each position, it just compiles that into a simplified version of the image. We can include multiple layers for this, but this one just has 2. This is the part in the project for the malaria project. You guys are going to write this part entirely on your own. We'll be here to help, but like, this is the part that's going to be blank, which is the dense part. So if you notice in Siddhesh's model, he had to write 28 by 28, which is the version that doesn't use the CNN because it's directly taking in the image. Here, flatten already knows what to do because the convolutional layers take care of reading in the input. These guys don't do much thinking, but they do like the understanding of the image part of it. And then these guys, the 128 nodes in the first dense layer, and then the 10 output nodes. That's where the weights and biases are being configured, to essentially process the image and see what's in it. So we're going to compile it. Model.summary is going to give us it's going to print out a summary which shows us how many parameters the model is going to train. None of these are ours to control. The model is going to work on them by itself. It's cool. It's like a human subconsciously tweaking their own neurons to learn something new. And there's a total of 421,642. Yeah. Are we good so far? I'm sorry, I forgot to ask earlier. Are we doing okay? How are we feeling? I'm like shoving so much information, so stop me, please, if there's any slowing down to be done. Okay, I'm gonna move on, but feel free to stop me if you're confused. So compiling the model, you've built the model object, you know what properties it has, and you're trying to compile it with a certain optimization algorithm. We're using Atom. We need a certain loss function. There's multiple. In linear regression, it's sort of like what Siddhesh mentioned with the slope, and that's one kind of machine learning. It's more like the statistical kind of machine learning. This is sort of more like, if we add a lot of layers here, we call that deep learning, which just means we're adding a ton of brain cells for it to use. And the model becomes deep. It just has a lot of layers. So we're compiling it. Metrics, we're using the accuracy metric. There's multiple. We can cover more on that later. Yes, Shanil just sent out the link for this. You can check it out later yourself if you want. It'll be helpful before you do the project if you go through this. Even if you don't, you'll still be fine, but it's just good. It's a good idea. So you compile the model with these three things: optimizer, loss function, and metrics. And there's multiple for each one of these. So you can pick if you know any, or we can actually, we'll figure that out. If we want you guys to change it, we will give you the resources so you can see what functions exist. Right, now batch size. Essentially the difference between a batch and an epoch. And this is something, oh yeah, this was my model from earlier. You guys notice this little slider here, batch size 5, 6, 7, 8, 10, whatever. It is essentially how many dots it is learning on in one bunch, which is just another word for batch. And it's just learning on 10 at a time until it finishes the whole data set once. Those are batches. And then if it goes through all the batches one more time, that's another epoch. So essentially, I think I've said this before, but when you read a chapter in a book, that's like a batch, right? It's one part of the book. When you read the book one time end to end, that's called an epoch. And the same way, right now we're getting it to read images in bunches of 32 at a time, and then it learns 32 at a time, and then it learns. And then it does the whole data set 5 times in 5 epochs. All right, so model.fit, this is the juicy stuff. This is where we're actually training the model. Keras makes it lovely, lovely syntax. What is fitting? If you recall in Siddhesh's diagram, I don't know if I can annotate. I think I can. Right, essentially he had a function, right? Which basically had predictions and actual values. And the model is supposed to try to figure out some sort of function that can match those values, but not be limited by those values. All right, wait, something's in the chat. Okay. So it wants to figure out the values without being bound by them. So it needs to learn from the textbook, but it shouldn't learn the textbook. That's probably the simplest way I can put it for now. We can go into more detail at another time, but that is what fitting does. If it learns too much from the textbook, we call it overfitting. If it learns too little, we call it underfitting. That's basically it. Okay. Darn, it's still there. Hang on. Clear all drawings. Okay. You can save the model and it just shows up as a file right there. That's just like if you want to save it to your personal Colab. What does the save do? When it went and trained all of its parameters, which are the weights and biases, it saves that configuration so that you can just take the same model and use it on different data, right? To see how it does across data sets. So we've trained it, and it looks like we have a really high accuracy on the training data, which is 99.47. And that's typically what CNNs do. They get you like all this crazy accuracy, but at the cost of a ton of computation. All right, going to testing. Look at that, 99% accuracy on test data. So for this purpose, it's good. In the industry, people usually raise eyebrows when you say your model is 99% successful, because usually things are like around 80 to 85. And then people start wondering if it crosses that, they'll be like, is your model trained on like the right data? And is it being tested on the right data? By right data, they're saying, did you sort of rig it to perform well with the data that you fed in? So then at that point, they like to give it like completely different data, maybe more modern, like current data. If it trained on something from a year ago, they'll test it on the data from today, and they'll see if the network still performs that well. And if it's 99%, then that's like $1 million. So that is the rundown of a CNN. Are there any questions through any of this?
So we're only learning like the part that's in the model, or
So your job in the project, and we're going to show you this next week, before you guys begin, is essentially just writing this part and then deciding some of these hyperparameters. And that's why we actually had you guys do this today, so that you decide how many neurons work. Learning rate is probably like, you only had it for this. You don't have that here. But the idea that you can change hyperparameters, that's what all of these are, to get a better performance. So you're mainly not worrying about the dense part of the network. We're writing the CNN part. Don't worry about it. The dense part and the optimizer and the loss function metric, we need accuracy. I will keep it that way. We can have you change the batch size as well. You can have it train on 10 at a time or 100 at a time, because there's a ton of images in the project. But yeah, and that's it. Everything else is pretty much the same. But this project is like serving two purposes. One is having you guys actually just say that you have successfully built a neural network. And the other is learning about sort of like the basics of how data is being handled before it goes in. The data science part of the malaria project is going to be a little more intricate than this, because MNIST is already a pretty clean data set. Malaria isn't, and there's ones that are way worse. So I have a question here. How do we know if it's over or underfitting? Usually they try to do something called regularization. I don't think that's the same thing as this regularization rate. This is a mathematical function that they apply, but they basically go through the network. I'm going to pull up the network, and they remove certain neurons. They'll be like, you there, get out. And the network is going to try to figure out how to do the same problem while missing that brain cell. And that way you'll know if it was overfitting, it was relying too heavily on that neuron to store certain information. It's sort of like, hey, you're walking too well. I'm going to like sprain one of your ankles to see how well you can still walk. It's kind of like that. So it sounds mean, but that's kind of how we test to make sure it actually knows how to walk. And it's not just, okay, in walking, there's really no way to cheat, but we know that it's not cheating by relying too much on one neuron. That's how we handle overfitting. Underfitting, we test it with more and more data, and we see how it does with huge volumes of data. If it does fine with like a small amount, that's okay, because most models do that. But when it gets to like big data, and I'm talking like millions and millions of entries in a database, right, being just fed in, you can tell if the thing is dumb. If it's so smart that it's dumb, if it has too many brain cells for it to properly understand, or if it has too few. So it's an art. I wouldn't call this a science. It's an art, being able to create the right neural network for the job with the right hyperparameters. But that's how you determine usually whether something is being overfit or underfit, being, is learning too well or learning too little. Is that through trying a bunch, or is there a way? Both. The way involves trying a bunch and then seeing, like, there are statistical metrics that you can use to assess a model. There are things like the confusion matrix. Maybe psychology students would know. This is the true positive, true negative, false negative thing. Even med students, anyone who's done any sort of thing with like bio and stuff would have seen this. I think you check if its prediction is right and if the ground truth, which is the label, is right. If those match, it's a true positive. Things like that. You have various statistical metrics, but they only can be measured after trying several. Learned in Fire 120. That's pretty cool.
Rohit,
Yes, Siddhesh.
Rohit, I'll take just 2 minutes and like
Okay.
I want to,
Do you want me to stop sharing the screen?
yeah.
Okay.
Okay, yeah. So as Rohit was saying, the CNN it's like a spotlight. So what exactly it does is like, I guess you can see better now. Yeah. So what this it actually does is like it just goes over this part. Okay. It goes over this part and like then focuses on this and then moves this window to this part and then takes the data and learns of it and then just goes to this part and so on, and it covers the whole thing like window by window, like in small windows. And like instead of like going in the whole thing in like one go. So how does it help it? Because like it's like you can consider it as a magnifying glass looking at something really small and like focusing on some detail in like some part, some corner of the image, and then like and slowly putting a magnifying glass on the whole thing and then just converting the data into one afterwards. That's the difference on how CNN works from difference in a feed forward network.
All right. Awesome. Yeah. So that's basically how the flashlight goes bit by bit. I mean, not bit like computing bit, but part by part. And it tries to identify different features. I'm going to put in a little link. It's a 60-second survey for us to know if you guys enjoyed today and what you think we could have done better, as well as it's an important question. Are you interested in doing the project? If you are, just hit yes. You do need to be here for sure in the next 2 weeks because this is a live thing. The project is going to be done live, like the TensorFlow Playground activity today. That's it. Any questions, feel free to stay back. Otherwise, we've kept you for a while. Sorry about the heavy session, but
Yeah, sorry.
hope it was fun. You are free. Be released into the wind. That doesn't sound right. You want to stop recording?